In the last lecture, we have seen how to represent a single phase transformer by approximate equivalent circuit, either referred to the primary or referred to the secondary. Now, it would have been convenient if we can derive a single equivalent circuit without being too concerned about whether it is referred to the primary or referred to the secondary. There are some practical advantages of having an equivalent circuit like that. The way we can do it is by converting this equivalent circuit to per unit equivalent circuit, where each parameter of the equivalent circuit and each variable are expressed in per units. How do we do that? In order to get a per unitized equivalent circuit, we have to define certain base quantities. Although the bases can be selected arbitrarily, the customary practice is to select the rated voltage of a given side of a transformer to be the base voltage. Therefore, the rated voltage of the primary will be the base voltage for the primary side variables and parameters. So, we call it V base 1 equal to rated voltage of the primary. Similarly, V base 2 will be the rated voltage of the secondary. Since in a transformer the kVA of the primary and the secondary are the same, therefore, there is only a single kVA base is the rated kVA of the transformer. From this basis, we can define the base currents I base 1 equal to kVA base divided by V base 1. Similarly, I base 2 equal to kVA base by V base 2. Next step, we can define a base impedance Z base 1 equal to V base 1 by I base 1, and this is the V base 1 square by kVA base and Z base 2 equal to V base 2 divided by I base 2 equal to V base 2 square by kVA base. Once we define these base quantities, a voltage in per unit can be written as V 1 in per unit equal to the actual value of V 1 divided by V 1 base, or rather V base 1. Similarly, V 2 in per unit will be equal to actual value of V 2 divided by V base 2. I 1 in per unit will be equal to actual value of I 1 divided by I base 1. Similarly, I 2 in per unit will be equal to I 2 divided by I base 2. any impedance, let us say R1 in per unit will be equal to actual value of R1 in ohms divided by Z base 1, and let us say X2 in per unit will be actual value of X2 in ohms divided by Z base 2. Now, how does our this defining these base quantities and per unit values help to achieve a single unique equivalent circuit of a transformer? Let us see. For that, let us consider the exact equivalent circuit of the transformer. Refer to the primary side. The set of equation that describes this equivalent circuit are V1 equal to R1 plus J X1 into I1 plus E1, E1 equal to R2 dash plus J X2 dash I2 dash plus V2 dash, and V2 dash equal to I2 dash ZL dash. Similarly, I0 equal to E1, these are all phasors, by R0 plus E1 by JXM, and I1 equal to I0 plus I2 dash. Now, let us convert them to equations in per unit variables and parameters. In order to do that, let us first divide the first the left hand side by the first equation by V base 1. So, becomes V1 by V base 1 equal to R1 plus J X1. Let us also divide I1 by I base 1 and since also multiply by I base 1 divided by V base 1 plus U1 by V base 1, but this is V1 per unit equal to V base 1 by I base 1 is Z base 1, and R1 plus J X1 by Z base 1 is R1 per unit plus J X1 per unit into I1 per unit plus E1 per unit. Similarly, by dividing the second equation by V base 1, we get the right hand side can be rewritten as but from our definition of the base quantities, equal to N1 by N2 and also applying these relations, we have E1 per unit equal to R2 plus Jx2 divided by Z base 2, that is R2 per unit plus Jx2 per unit multiplied by I2 by I2 base is I2 per unit N2 by N1 cancels with 1 of N1 by N2 square. So, this becomes N1 by N2 into V base 2 by V base 1, which is 1. n1 by n2 into v base 2 by v base 1, which is equal to 1. Therefore, this is what we get from this, and on this side we have n1 by n2 into v base 2 by v base 1, which is again 1, and we are left with only v 2 per unit. So, we see that we arrive at the same equation in per unit. Similarly, we can apply similar thing to the last equation, v 2 dash bar by v base 2 equal to I 2 dash bar by I base 2 into I base 2 by v base 2 into Z L dash, but v 2 dash equal to n 2 by n 1 by n 2 into v 2 divided by v base 2 plus equal to I 2 dash is n 2 by n 1 into I 2 divided by I base 2 into 1 by Z base 2 into Z L into n 1 by n 2 square, or n 1 by n 2 v 2 per unit equal to Z L per unit into I 2 per unit into n 1 by n 2. Cancelling n 1 by n 2 from both sides, we have the per unit relation v 2 per unit equal to Z L per unit into I 2 per unit. Coming to the fourth equation, I 0 equal to E 1 by R 0 plus E 1 by J x m. One can write I 0 by I base 1 equal to E 1 bar by V base 1 into V base 1 by I base 1 into 1 by R 0 plus E 1 bar by V base 1 into V base 1 by I base 1 into 1 by J x n, or I 0 per unit equal to E 1 per unit divided by R 0 per unit plus E1 per unit divided by J xm per unit. For the last equation, I1 equal to I0 plus I2 dash, one can write I1 bar by I base 1 equal to I0 bar by I base 1 plus N2 by N1 I2 divided by I base 2 into I base 2 by I base 1 or I1 per unit equal to I0 per unit plus I2 per unit, since N2 by N1 into I base 2 by I base 1 is unity. Therefore, the complete set of equations in per unit can be written as E1 per unit equal to R2 per unit plus J x2 per unit into I2 per unit plus V2 per unit, V2 per unit equal to I2 per unit into ZL per unit, I0 per unit equal to U1 per unit by R0 per unit plus E1 per unit by J xm per unit, and I1 per unit equal to I0 per unit plus I2 per unit. This is a unit set of equation. The R1 and R2 expressed in per units with respect to their base are same on both sides. Therefore, the equivalence per unit equivalent circuit, exact equivalent circuit will be similar to our familiar exact equivalent circuit, except that now all parameters are to be expressed in per units. all variables are also expressed in per units. And once they are expressed in per units, there is no need to refer these parameters to one side or the other by any turns ratio. Now, this is advantageous in many situations. It may not be so apparent when we consider a single transformer. However, it will be easy to understand if we have several such transformer. For example, in a power system, suppose we have a source V1 which supplies some transformer, supplies another transformer which may in turn supply few more transformers. Which may in turn supply the load. In such a situation, if we have to refer every impedance to a single side in order to solve the problem, it will be too complicated, and for very large power system with literally tens of thousands of transformers, it will become completely impossible. Under such situation, representing the parameters of the transformer or the load or the transmission line in per unit system is advantageous, because it does not involve referring the impedances to a single side. Therefore, for almost all practical calculation, the transformer parameters are normally represented in per unit. In fact, just as with exact parameters, the approximate equivalent circuit of the transformer can also be drawn in per unit. Where Req per unit is simply R1 per unit plus R2 per unit. Similarly, Xeq per unit equal to X1 per unit plus X2 per unit. Now, a transformer equivalent circuit, whether expressed in actual parameters referred to the primary or secondary, or expressed in the per unit parameter, will be useful only if one knows the values of the parameter. Now, therefore, it is important to be able to determine the transformer equivalent circuit parameters either from the design data or by carrying out certain tests. It is possible to estimate the parameters of the transformer from the dimensions and the design data. However, in most cases the user will not have access to such design data, and also the design data gives a first approximation of these parameters. In order to get more accurate values, the user must conduct certain tests on the transformer. There are two tests that are normally used to find out the equivalent circuit parameters of the transformer. One is no load test, which finds out the shunt branch parameters R0 and Xm are connected across the source. So, these are called the shunt branch parameters. Similarly, a short circuit test to find out the approximate equivalent circuit parameter Req and Xeq, which are called the series branch parameter. We will see how these tests are done. Let us first concentrate on no load test. In order to perform a no load test, you take the transformer under test, keep one side open connected to a voltmeter, AC voltmeter. On the other side, you connect an ammeter, a wattmeter, and normally supply it from what we call a single phase variac, which can supply at least the rated voltage of this side of the transformer. In order to do the no load test, the variac is started from 0 voltage position, then the power is applied, the voltage supplied by the variac is slowly raised till the voltmeter connected on the other side reads the rated voltage of this side. Under that condition, we take the readings of voltage V, there is also another voltmeter connected here, let us call it V1, this is V2. We take the readings of V1, this current I0, which is the no load current, and the wattmeter reading W0. From this, we will see how to find out the shunt branch parameters very shortly. But before that, let us be a little more specific about how to choose this equipment and which side should we choose. Should we keep the high voltage side open and apply voltage to the low voltage side, or the other way around? Now, theoretically it does not make a difference. It can be used at the supply can be given to either side of the transformer, and the per unit parameters determined will be the same. However, there are some practical limitations. For example, this test is to be performed by applying rated voltage of the side, that is the V1 should read the rated voltage of the transformer on this side. So, if this is the HV side, then I will need a variac which can apply the rated high voltage across this transformer, and for high voltages this may be really large in kilovolts. That is one problem. The meters should also be rated at the high voltage winding rating of the transformer. The second problem is, since the transformer is in open circuit condition, it draws only no load current. Now, the no load current of a well designed transformer is less than 5% of the rated full load current. As such, the rated full load current of the high voltage side is much lower than that of the low voltage side. No load current being even only 5% of the high voltage rated current, its value will be really small, and it will be difficult to get a accurate enough ammeter to read that, since as we will see the same ammeter will also be required to read the rated current in a later test. So, it is usually preferred to supply the voltage to the low voltage side of the transformer and keep the high voltage side open. Therefore, no load tests are usually performed on the low voltage side. One should be also careful about choosing the wattmeter. The wattmeter potential coil should be rated at the rated voltage of the low voltage side of the transformer. However, the current flowing through the wattmeter current coil will only be the no load coil, no load current. Therefore, the current rating of the current coil of the wattmeter should be low. Not only that, at no load the transformer power factor is very poor, it is almost 0. So, one must use a low power factor wattmeter, LPF wattmeter, to get reliable readings. Now, let us see how we use the no load test data to find out the shunt branch parameters. At no load, the transformer equivalent circuit, the approximate equivalent circuit of the transformer looks like this. Since the load is open, these terminals are open, we are applying voltage here, voltage of V1 here, the current drawn is I0 and the power reading is W0. So, if I draw the phasor diagram, then this is V1, this is the no load current I0, hence the component in phase with V1 is IC flowing through Rm, and the component perpendicular to V1 and lagging it by 90 degree is the current being drawn by the magnetizing branch Im. Hence, we can write, this is the no load power factor angle phi 0. We can write Rm equal to V1 by IC equal to V1 by I0 cos phi 0 and Xm equal to V1 by Im equal to V1 by I0 sin phi 0. So, from the meters V1 I read the voltage, from the meter ammeter I read I0, and from the wattmeter we read the power reading W0. So, what is cos phi 0? Now, W0 equal to V1 I0 cos phi 0. Therefore, cos phi 0 equal to W0 by V1 I0, and sin phi 0 equal to square root 1 minus cos phi 0 square cos square phi 0. Therefore, Rm equal to V1 by I0 cos phi 0 equal to V1 square by W0 and Xm equal to V1 divided by I0 sin where sin phi 0 equal to square root 1 minus W0 square by V1 square I0 square. Now, since the test is performed on the LV side, Rm and Xm values that are obtained, these will be referred to LV side. Now, if we want to convert them into per unit, then Rm per unit will be Rm divided by Z base of the LV side. Now, Z base of the LV side equal to V of the transformer LV side rated divided by I base of the LV side. Now, I base of the LV side equal to KVA base divided by LV side voltage base. Therefore, Z base LV side equal to VLV rated square divided by KVA rated hence RPU will be equal to Rm into kVA, rated kVA of the transformer divided by rated LV voltage square. Similarly, Xm per unit will be Xm into rated kVA of the transformer divided to by VLV square rated. So, thus we can find out the actual shunt branch parameter of the transformer referred to the LV side and convert them to per unit parameter with LV side base quantities. So, of the parameters of the equivalent circuit of a transformer, approximate equivalent circuit parameters we have found R 0 and Xm. Next, we have to find out the parameters Req and Xeq, and this is done by short circuit test. In short circuit test, what we do? We take the single phase transformer, and short one of the sides. On the other side, again we connect a ammeter, we connect a wattmeter, and supply this again from a variac. It can be the same variac or some other variac. Again, as before, in the case of no load test, question arises which side should be shorted and which side the supply should be applied. Now, the requirement for short circuit test is that it should be performed at rated current, which means the ammeter should read the rated current of the side it is connected. Obviously, if this is the LV side, then we will have to supply a very large current, because LV side rated current is much larger than the HV side rated current. Hence, normally the short circuit test is performed on the HV side. So, this is the HV side and the LV side is shorted. Again, coming to the question of wattmeter, the wattmeter current coil now should be capable of carrying the rated HV side current. However, the voltage required to circulate rated HV side current when the LV side is short circuited is very small. It is usually between 5 to 10% of the rated HV side voltage, and that is another reason why the short circuit test is performed on the HV side, because one does not need to apply the full HV voltage, only a very small fraction of the HV voltage is required. But the wattmeter potential coil should be sensitive enough to give accurate reading at that small voltage. At no load, we have said that the power factor is very poor, it is close to 0. At short circuit, power factor is still poor, but may not be as bad as that in the case of a open circuit case. Hence, a normal wattmeter can possibly be used, but in some very special cases this test may also require a LPF wattmeter, but we will assume a normal wattmeter will do. Now, how do we find out the series branch parameter from the short circuit test? For that, let us draw the approximate equivalent circuit under short circuit condition. Now, this is the equivalent winding resistance and this is the equivalent leakage resistance. Now, refer to the HV side because the supply is applied to the HV side and this is the magnetization branch. Again refer to the HV side. At this point, and let us say this is the voltage applied V short circuit, I short circuit, and the wattmeter reading is W short circuit. Now, even at when Vs is at its rated value, we have seen the no load current I0 is 5 to 7% of the rated current, that is I0 if it is connected to the HV side, then even if we apply rated voltage, then I0 is only 5 to 7% of Is. Therefore, when we reduce Vs in order to and short the low voltage side, if we restrict the Is to its rated value, the voltage that will be required for that will send very negligible current through the magnetization branch, and hence for all practical purpose the magnetization branch can be neglected during short circuit. Then we have very simple relation, the short circuit impedance Zs equal to square root of Req square plus Xeq square. This is given by V short circuit divided by I short circuit the power loss during short circuit is assumed to be entirely due to the series resistance. Therefore, Ws equal to Is square Req, hence Req equal to Ws divided by Is square, hence Xeq equal to square root Zs square minus Req square. Just as in this, Req and Xeq are now found referred to the HV side. Please remember the shunt branch parameters Rm and Jxm were found referred to the LV side. It is possible to either refer Rm-Xm to the HV side or Req and Xeq to the LV side by the appropriate turns ratio and arrive at a complete approximate equivalent circuit of the transformer referred to either HV side or LV side. However, as I have mentioned earlier, it is customary to represent this parameter in per unit, and Req for example can be represented in per unit as Req that we have got from the test into kVA rated of the transformer divided by VHV square, now rated HV voltage square. Similarly, Xeq in per unit will be the value obtained from the test into kVA rated of the transformer divided by rated HV voltage square of the transformer. Hence, the approximate equivalent circuit of the transformer in per unit will look like